Hello there, and welcome to this quiet corner of the universe where science unfolds slowly and wonder is allowed to breathe. Tonight, we're not rushing anywhere. We're not chasing deadlines or cramming for exams. Instead, we're going to drift toward the coldest place imaginable, a temperature so extreme it exists more as an idea than a destination. We're talking about absolute zero, minus 459.67 degrees Fahrenheit, a place where the very atoms that make up everything around you would slow to an almost perfect stillness. If you're here because sleep is calling but your mind is still restless, you've found the right place. If you're here because you love those moments when science reveals something so beautiful, it feels like poetry, you're home. And if you're here because you've always wondered what would happen if we could somehow steal all the heat from the universe itself, well, settle in. Because we're about to explore a realm where quantum mechanics dances with thermodynamics, where the impossible becomes inevitable, and where the coldest temperatures reveal some of the most surprising truths about how reality actually works. Before we begin our journey toward the ultimate cold, let me ask you something. Right now, wherever you are, you're surrounded by motion. Not just the obvious kind, the turning of the earth or the flow of air through your room, but motion at every scale. The molecules in the air are bouncing off each other billions of times per second. The electrons in your body are spinning in their orbits. Even the atoms in the chair you're sitting on are vibrating with thermal energy. All of this motion, this constant dance of particles, is what we call temperature. Heat isn't a thing, it's movement. And the more movement, the hotter something gets. So what happens when that movement slows down? What happens when we take away the energy that drives all this microscopic chaos? What happens when we approach the theoretical limit where motion itself might finally stop? That's the question that has fascinated scientists for centuries, and the answers they found are stranger and more beautiful than anyone could have predicted. The story begins not with complex equations or expensive laboratory equipment, but with a simple observation that anyone can make. If you've ever pumped up a bicycle tire, you know that the pump gets warm as you compress the air inside. If you've ever felt the cool sensation of rubbing alcohol evaporating from your skin, you've experienced the opposite effect. Temperature and motion are connected in ways that seem almost magical until you understand what's really happening at the atomic level. In the 1700s, scientists began to notice something curious about gases. When you cool them down, they contract. When you heat them up, they expand. This seems obvious now, but back then it raised a profound question. If gases keep contracting as they get colder, what happens when you keep cooling them indefinitely? Where does it end? Some brilliant minds started to imagine that there might be a point where gas would contract to zero volume, a temperature so cold that matter itself would reach some kind of fundamental limit. This wasn't just idle speculation. It was the beginning of our understanding of absolute zero, though they didn't call it that yet. They were seeing the first hints that temperature isn't an endless scale stretching infinitely in both directions. There's a bottom, a place where the cosmic thermostat can't be turned any lower. And getting there, it turns out, would require us to understand things about the universe that wouldn't be discovered for another century. The path toward absolute zero isn't just a story about temperature, it's a story about the fundamental nature of reality itself. Because as we'll discover, when you start removing heat from matter, when you begin to slow down the endless dance of atoms and molecules, you don't just get colder stuff, you get entirely new states of matter that behave in ways that seem to violate everything we think we know about how the world works. Imagine for a moment a liquid that flows uphill, a liquid that can climb out of its container, defying gravity as if it were nothing more than a suggestion. Imagine electrical current that flows forever without losing any energy, creating magnetic fields so perfect they can levitate trains or peer inside the human body with impossible clarity. Imagine atoms that stop behaving like individual particles and merge into something that acts like a single, giant quantum object visible to the naked eye. These aren't science fiction fantasies. They're real phenomena that emerge when matter approaches absolute zero. They're windows into a realm where quantum mechanics, usually hidden in the microscopic world, becomes large enough to touch, to see, to experience directly. And they all depend on one simple principle. Take away enough heat, slow down enough motion, and the strange rules that govern the very small start to govern the very large. But here's where the story gets really interesting. Absolute zero isn't just hard to reach. According to the fundamental laws of physics, it's impossible to reach completely. Not because we don't have good enough refrigerators, not because we haven't figured out the right techniques, but because the universe itself won't allow it. There's something built into the very fabric of reality that prevents matter from ever becoming perfectly still. Even at absolute zero, even at the coldest possible temperature, there's still motion, still energy, still something happening. This might sound disappointing at first. If we can never actually get there, why does it matter? But this impossibility is actually one of the most beautiful aspects of the story. Because in trying to reach absolute zero, in getting incredibly close, but never quite arriving, we've discovered some of the most profound truths about how the universe works. We've found that the boundary between the possible and impossible isn't a wall. It's more like a horizon, always approachable but never quite reachable. And the view from near that horizon reveals landscapes we never knew existed. The number itself, minus 459.67 degrees Fahrenheit, or minus 273.15 degrees Celsius, or 0 on the Kelvin scale, isn't arbitrary. It's written into the structure of space and time. It's the temperature at which, according to classical physics, all thermal motion would cease. It's the point where pressure from an ideal gas would drop to 0, where entropy reaches its minimum value, where the thermal energy that drives so much of what we see around us finally runs out. But as we'll discover, classical physics only tells part of the story. When we get close enough to absolute zero, quantum mechanics takes over. And quantum mechanics has very different ideas about what it means for something to be perfectly still. In the quantum world, uncertainty isn't just a limitation of our measurements, it's a fundamental property of reality. And that uncertainty means that even at absolute zero, even when thermal motion has been eliminated, there's still something called zero-point energy, a kind of motion that can never be removed, never be eliminated, never be turned off. This zero-point energy is what keeps liquid helium from freezing solid, even when cooled to temperatures that would solidify every other substance in the universe. It's what allows electrons in superconductors to flow without resistance. It's what makes possible the strange quantum states that exist only in the deepest cold, states where individual atoms lose their identity and merge into collective quantum objects that behave more like waves than particles. The journey toward absolute zero has been one of the great scientific adventures of the past 2 centuries. It's required the development of entirely new technologies, new ways of thinking about heat and cold, new mathematical frameworks for understanding the behavior of matter at extreme conditions. Along the way, it's given us everything from the magnetic resonance imaging machines that can see inside our bodies to the quantum computers that might revolutionize technology in ways we're only beginning to imagine. But perhaps most importantly, the story of absolute zero is a reminder that the universe is far stranger and more wonderful than our everyday experience suggests. The air around you right now is filled with molecules moving at hundreds of miles per hour. The solid table next to you is actually mostly empty space, with atoms vibrating in precise crystalline patterns. And somewhere in laboratories around the world, scientists are creating conditions colder than anything that exists naturally in the entire cosmos, places where matter reveals secrets that have been hidden since the beginning of time. Tonight, as we explore this landscape of ultimate cold, we're not just learning about temperature, we're learning about the deep structures that underlie everything we see and touch and experience. We're discovering that the familiar world of warm bodies and flowing liquids and solid objects is just one layer of a much richer reality. And we're finding that sometimes to understand what something really is, you have to take it apart completely. You have to remove everything that can be removed, cool everything that can be cooled, slow everything that can be slowed, until only the most fundamental aspects remain. So let's begin this journey together. Let's follow the path toward the coldest possible temperature and see what secrets it reveals about the nature of matter, energy, and the quantum mechanical foundation of everything that exists. Let's discover what happens when the universe itself becomes our laboratory and absolute zero becomes our guide to understanding the impossible made real. The mathematics of absolute zero began to reveal itself in the early 1800s, when a French physicist named Jacques Charles was studying how gases behave when heated and cooled. What he discovered was elegant in its simplicity and profound in its implications. For every degree you cool a gas, its volume decreases by a predictable fraction. Heat it up, and it expands by that same predictable amount. It was as if the universe had built a mathematical relationship directly into matter itself. But Charles noticed something else, something that would echo through the centuries of physics that followed. If you extended this pattern backward, if you imagined cooling a gas more and more, the mathematics suggested that at some specific temperature, the gas would contract to zero volume. Not nearly zero, not almost zero, exactly zero. The equation pointed to a precise moment where matter would reach some kind of fundamental boundary. This temperature, when Charles calculated it out, came to roughly minus 460 degrees Fahrenheit. It was a number that emerged not from philosophy or speculation, but from pure observation of how real gases behaved in real experiments. The universe seemed to be telling us through the language of mathematics that there was a bottom to the temperature scale, a place beyond which coldness could not go. Of course, real gases don't actually shrink to zero volume. They condense into liquids first, then freeze into solids. But the mathematical relationship Charles discovered was pointing to something deeper. It was revealing that temperature isn't just a measure of how hot or cold something feels. It's a measure of the internal energy of matter itself. And that energy has limits. This insight opened a doorway to understanding heat in an entirely new way. Temperature, it turned out, is really a measure of average kinetic energy. Every molecule of air around you right now is moving, bouncing, vibrating with a particular amount of motion. The faster that motion, the higher the temperature. The slower that motion, the colder things become. And if you could somehow slow that motion down completely, if you could make every molecule perfectly still, you would reach absolute zero. But even as this picture was taking shape, scientists were discovering that the reality was far more complex and beautiful than anyone had imagined. In the 1840s, a Scottish physicist named William Thomson, later known as Lord Kelvin, took Charles's work and expanded it into something revolutionary. He created a new temperature scale, one that started at absolute zero and counted upward from there. No more negative numbers, no more arbitrary starting points, just pure fundamental temperature measured from the coldest possible point in the universe. The Kelvin scale, as it came to be known, revealed something remarkable about the nature of cold. Absolute zero wasn't just another temperature. It was temperature zero, the starting point from which all thermal energy is measured. It was like discovering that there's a fundamental ground floor to the universe's energy, a basement below which you simply cannot go. This wasn't merely a theoretical curiosity. Understanding absolute zero began to unlock practical mysteries that had puzzled scientists for generations. Why do some materials conduct electricity better than others? Why do certain substances remain liquid at temperatures that should freeze them solid? Why does matter sometimes behave in ways that seem to violate the basic rules of physics? The answers, it turned out, were hidden in the quantum mechanical world that emerges when matter approaches its coldest possible state. But to understand that world, we first need to appreciate just how different absolute zero is from any cold we've ever experienced. The coldest natural temperature on Earth might be found in Antarctica during winter, perhaps minus 130 degrees Fahrenheit. That sounds impossibly cold until you realize it's still more than 300 degrees warmer than absolute zero. The coldest natural place we know of in the entire universe is a nebula called the Boomerang Nebula, where expanding gas has cooled to about minus 458 degrees Fahrenheit. Even that cosmic refrigerator is still a degree and a half away from absolute zero. These numbers help put the extremeness of absolute zero into perspective. We're not talking about the kind of cold that makes you shiver or that freezes water into ice. We're talking about a cold so profound that it changes the fundamental rules by which matter behaves. At absolute zero, things don't just get colder, they become something else entirely. Consider what happens to the air around you as it cools. At room temperature, the molecules of nitrogen and oxygen are racing around at about 1,000 miles per hour, colliding with each other billions of times every second. Cool that air down to the temperature of liquid nitrogen, and those molecules slow to perhaps 600 miles per hour. Still incredibly fast, but noticeably reduced. Now imagine cooling that air further, down toward absolute zero. As the temperature drops, the molecular motion continues to slow, but something strange begins to happen. The normal rules of gas behavior start to break down. The classical physics that works so well at everyday temperatures begins to give way to quantum mechanics. And in the quantum world, things work very differently. At temperatures within a few degrees of absolute zero, individual atoms begin to lose their separate identities. They start to merge into collective quantum states, where the boundary between one particle and another becomes blurred. Groups of atoms begin to behave like single, giant quantum objects. It's as if the individual notes of an orchestra gradually blend into a single, pure chord that resonates with perfect harmony. This isn't just a metaphor. At these extreme temperatures, matter literally begins to exhibit wave-like properties that are normally invisible. Atoms that should behave like tiny billiard balls instead start to act like ripples on a pond, interfering with each other in patterns that create entirely new states of matter. One of the most striking examples of this quantum behavior is something called a Bose-Einstein condensate. Predicted by Einstein in the 1920s, but not created in a laboratory until 1995, a Bose-Einstein condensate forms when a gas of certain types of atoms is cooled to within a few millionths of a degree of absolute zero. At that point, thousands or even millions of individual atoms suddenly collapse into the same quantum state. They become, in effect, a single atom the size of a grain of sand. The creation of the first Bose-Einstein condensate was like watching science fiction become reality. Researchers used lasers and magnetic fields to trap and cool a tiny cloud of rubidium atoms. As the temperature dropped lower and lower, approaching absolute zero, the individual atoms gradually merged into something that had never been seen before, a state of matter so unusual that it seemed to glow with its own internal quantum light. What makes Bose-Einstein condensates so remarkable isn't just their strangeness. It's that they reveal quantum mechanics operating on a scale large enough for us to observe directly. Normally, quantum effects are hidden in the microscopic world of individual atoms and subatomic particles. But near absolute zero, those quantum effects expand outward until they become visible, measurable, manipulable. This amplification of quantum behavior near absolute zero has led to some of the most important technological breakthroughs of the modern era. The superconducting magnets that make MRI machines possible depend on materials cooled to within a few degrees of absolute zero. The quantum computers that might revolutionize information processing require their delicate quantum states to be protected by temperatures colder than deep space. But perhaps the most beautiful example of quantum behavior at extreme cold is found in liquid helium. Helium is unique among all the elements in the universe. Every other substance, when cooled sufficiently, will eventually freeze into a solid. Ice, frozen nitrogen, solidified hydrogen, even frozen air. But helium refuses to cooperate. At normal atmospheric pressure, helium remains liquid no matter how cold you make it. You can cool it to within a tiny fraction of a degree from absolute zero, and it will still flow like a liquid. This isn't because helium is stubborn or unusual in any chemical sense. It's because of quantum mechanics. The zero-point energy built into the quantum structure of helium atoms is so large that it prevents them from settling into the ordered arrangement that characterizes a solid. This quantum effect creates one of the most beautiful demonstrations of physics you can imagine. Liquid helium near absolute zero doesn't just remain liquid, it becomes something called a superfluid, a state of matter that flows without any friction whatsoever. Superfluid helium can flow up the sides of its container, over the rim, and down the outside as if gravity were just a gentle suggestion rather than a fundamental force. Watching superfluid helium in action is like watching the laws of physics take on a dreamlike quality. The liquid moves with perfect smoothness, creating fountains that seem to violate conservation of energy, flows that appear to run uphill, and currents that continue forever without slowing down. It's matter behaving more like a ghost than a substance, guided by quantum rules that operate on scales large enough to see with the naked eye. The strange behavior of superfluid helium reveals something profound about the quantum world that exists just beneath the surface of everyday reality. At absolute zero, the quantum mechanical properties that are usually hidden become the dominant features of how matter behaves. The uncertainty principle, wave-particle duality, quantum entanglement, all of these abstract concepts become concrete, observable phenomena. This is why absolute zero matters so much to our understanding of the universe. It's not just an extreme temperature, it's a window into the fundamental quantum nature of reality itself. By approaching absolute zero, by creating the coldest conditions possible, we're not just making things very cold. We're stripping away the thermal noise that usually obscures the quantum mechanical foundation of everything that exists. In those ultra-cold laboratories scattered around the world, where temperatures approach absolute zero, scientists are essentially time-traveling back to the earliest moments of the universe, when thermal energy was so low that quantum effects dominated everything. They're creating conditions that allow us to see matter as it truly is, beneath all the motion and heat and chaos of the everyday world. And what they're finding there, in that realm of ultimate cold, is changing our understanding of everything from the nature of consciousness to the possibility of room temperature superconductors to the quantum computers that might one day simulate entire universes. The journey toward absolute zero isn't just about reaching the coldest possible temperature. It's about discovering the deepest possible truths about the reality we inhabit. The deeper we venture into this realm of ultimate cold, the more we encounter phenomena that challenge everything we thought we knew about the nature of existence itself. Because at these temperatures approaching the very floor of the universe's thermal basement, matter doesn't just behave strangely. It begins to reveal secrets that have been hidden since the dawn of time. Consider for a moment what happens inside the atoms themselves as we approach absolute zero. We tend to think of atoms as tiny solar systems, with electrons orbiting a central nucleus like planets around a sun. But this picture, comfortable as it is, dissolves completely in the quantum world of extreme cold. Near absolute zero, electrons don't orbit anything. They exist in probability clouds, in states of quantum superposition, where they are simultaneously everywhere and nowhere until the moment we try to observe them. But here's where it gets truly remarkable. Even at absolute zero, even when we've removed every possible bit of thermal energy from a system, those electrons keep moving, not because they're warm, not because there's any heat left to drive their motion, but because the universe itself won't allow them to stop completely. This is the strange realm of zero-point energy, where the Heisenberg uncertainty principle ensures that perfect stillness remains forever out of reach. The the uncertainty principle tells us something profound about the nature of reality. It says that you cannot know both the exact position and the exact momentum of any particle simultaneously. If an electron were to become perfectly still at absolute zero, we would know its momentum exactly. It would be zero. But that perfect knowledge would make its position completely unknown. The electron would have to be everywhere at once, spread out across the entire universe. So instead, even at absolute zero, electrons retain what physicists call zero-point motion. They vibrate with the minimum energy required by quantum mechanics, creating a kind of quantum jitteriness that can never be eliminated. It's as if the universe has a built-in restlessness, a fundamental inability to ever become perfectly calm and still. This zero-point energy isn't just a theoretical curiosity. It has real, measurable effects that shape the world around us in ways we're only beginning to understand. It's what keeps liquid helium flowing even at temperatures that would freeze every other substance in the universe solid. It's what allows certain materials to conduct electricity with perfect efficiency when cooled to near absolute zero. And it's what makes possible some of the most exotic states of matter that scientists have ever discovered. One of these exotic states emerges in metals cooled to within a few degrees of absolute zero. At these temperatures, something extraordinary happens to the electrons that carry electrical current. Instead of bouncing chaotically off atoms and losing energy as heat, they begin to pair up in a quantum mechanical dance that allows them to flow through the material with absolutely no resistance whatsoever. This phenomenon, called superconductivity, was first discovered in 1911 when a Dutch physicist named Heike Kamerlingh-Onnes was studying the electrical properties of mercury cooled with liquid helium. As the temperature dropped below a critical threshold, the electrical resistance suddenly vanished completely. Not reduced, not minimized, but eliminated entirely. Current flowing through the superconducting mercury could continue forever without losing any energy at all. The implications of this discovery were staggering. Here was a material that could conduct electricity with perfect efficiency, creating magnetic fields of unprecedented strength and stability. But superconductivity wasn't just about better electrical circuits. It was a window into a quantum world where electrons stop behaving like individual particles and start acting like a single, coherent quantum fluid. In a superconductor, electrons pair up despite their mutual electrical repulsion, forming what physicists call Cooper pairs. These pairs move through the material like dancers in perfect synchronization, never colliding with atoms, never losing energy to friction. It's as if the entire electron population becomes a single quantum object, flowing with the grace and precision of a perfectly choreographed ballet. The magnetic properties of superconductors are even more remarkable than their electrical behavior. A superconductor doesn't just conduct electricity without resistance, it actively expels magnetic fields from its interior, creating a phenomenon known as the Meissner effect. Place a magnet above a superconductor cooled below its critical temperature, and the magnet will float in mid-air, held aloft by the superconductor's perfect diamagnetism. This magnetic levitation isn't just a spectacular demonstration. It's the foundation for technologies that are revolutionizing everything from medical imaging to transportation. The powerful magnetic fields generated by superconducting magnets make possible the detailed views inside the human body provided by MRI machines. High-speed trains float above their tracks on cushions of magnetic fields generated by superconducting coils. And in laboratories around the world, superconducting magnets create the intense fields needed to confine the superhot plasmas that might one day power fusion reactors. But perhaps the most ambitious application of superconductivity lies in the realm of quantum computing. These revolutionary machines depend on maintaining delicate quantum states that can exist in multiple conditions simultaneously. At everyday temperatures, thermal noise destroys these fragile quantum states almost instantly. But cooled to within a few thousandths of a degree of absolute zero, superconducting circuits can maintain quantum coherence long enough to perform calculations that would take conventional computers millions of years to complete. The quantum computers of today are like the room-sized electronic computers of the 1940s, primitive by the standards of what's coming, but revolutionary in their implications. They operate in chambers cooled colder than interstellar space, where quantum mechanics becomes the dominant force shaping how information is processed and stored. In these machines, the strange rules of quantum superposition and entanglement that normally operate only at the atomic scale are harnessed to solve problems that classical physics says should be impossible. Yet even as we celebrate these technological marvels, we must remember that they all depend on a fundamental impossibility. We can never actually reach absolute zero. The third law of thermodynamics tells us that it would require an infinite number of steps, an infinite amount of time, and an infinite amount of energy to remove the last traces of thermal motion from any material system. This impossibility isn't a limitation of our technology or our understanding. It's built into the very structure of the universe. As we approach absolute zero, each additional degree of cooling becomes exponentially more difficult. The closer we get, the harder it becomes to extract that final bit of heat. It's like trying to climb a mountain that grows taller with every step you take toward the summit. But in some ways, this impossibility is more beautiful than any achievement could be. Because in our attempts to reach absolute zero, in pushing the boundaries of how cold we can make matter, we've discovered realms of physics that we never knew existed. We've found states of matter that seem to violate the basic rules of how things should behave. We've created conditions that allow quantum mechanics to operate on scales large enough for human beings to observe and manipulate directly. The laboratories where scientists approach absolute zero are among the most sophisticated and precise instruments ever created by human civilization. They use techniques like laser cooling, where beams of light are used to slow down individual atoms by hitting them with photons traveling in the opposite direction. They employ magnetic trapping, where carefully controlled magnetic fields hold clouds of ultra-cold atoms suspended in perfect vacuum. And they utilize dilution refrigeration, where the quantum properties of different isotopes of helium are exploited to reach temperatures billions of times colder than the depths of space. These techniques have allowed researchers to cool small samples of matter to temperatures measured in billionths of a degree above absolute zero. In some experiments, scientists have achieved temperatures so low that the thermal motion of atoms slows to less than a centimeter per second. At these temperatures, quantum effects that are normally invisible become the dominant features of how matter behaves. One of the most remarkable discoveries to emerge from these ultra-cold laboratories is that atoms cooled to near absolute zero can be made to form structures that exist in multiple states simultaneously. These quantum superposition states allow single atoms to be in two places at once, to spin in both directions simultaneously, to exist in conditions that classical physics says are impossible. But the strangeness doesn't stop there. When multiple atoms are cooled together to these extreme temperatures, they can become quantum entangled, creating connections between particles that persist even when they are separated by vast distances. Einstein famously called this spooky action at a distance, but experiments at near absolute zero have proven that quantum entanglement is not just real, but controllable and useful. These quantum phenomena, revealed in their full glory only at temperatures approaching absolute zero, are leading to technologies that would have seemed like magic just a few decades ago. Quantum sensors that can detect gravitational waves rippling through space-time. Quantum communication systems that are theoretically impossible to hack or intercept. And quantum simulators that can model complex physical systems by creating artificial versions of them using ultra-cold atoms. The story of absolute zero is ultimately a story about limits and what lies beyond them. It's about the human drive to push boundaries, to explore extremes, to discover what happens when you take something as fundamental as temperature and stretch it to its absolute limits. And what we've found there, in that realm of ultimate cold, is that the universe is far stranger and more wonderful than our everyday experience could ever suggest. In those laboratories where matter approaches absolute zero, where quantum mechanics becomes visible to the naked eye, where the impossible becomes routine, scientists are not just studying physics. They're exploring the deepest structures of reality itself. They are discovering that the familiar world of solid objects and flowing liquids and warm bodies is just the surface layer of a much richer and more complex universe. And perhaps most remarkably of all, they're finding that the journey toward absolute zero, toward that unreachable destination, is revealing truths about the nature of existence that we are only beginning to comprehend. The coldest temperatures in the universe are teaching us about the warmth of quantum entanglement, the heat of superconductivity, and the energy that remains even when everything else has been stripped away. So as we continue this exploration together, as we follow the path toward the coldest possible temperature, remember that we are not just learning about physics. We are discovering the hidden architecture of the cosmos, the quantum mechanical foundation upon which everything we see and touch and experience is built. We are finding that even in the deepest cold, even at the very edge of absolute stillness, the universe continues to surprise us with its beauty, its complexity, and its endless capacity for wonder. The pursuit of absolute zero has taken us to places that exist only in the most sophisticated laboratories on Earth. But the phenomena we've discovered there aren't confined to scientific research. They're woven into the fabric of the universe itself, operating at scales from the cosmic to the subatomic, revealing patterns that connect the smallest quantum effects to the largest structures in space. Consider the cosmic microwave background, that faint radiation left over from the Big Bang that permeates all of space. This ancient light has been cooling for nearly 14 billion years, and today it maintains an average temperature of about 2.7 Kelvin, just a few degrees above absolute zero. In essence, the entire universe is slowly approaching absolute zero as it expands and cools, carrying all of us along on this cosmic journey toward ultimate cold. But even in this cooling cosmos, there are pockets where temperatures drop far below the cosmic average. In the depths of interstellar space, in the shadows of distant nebulae, natural processes create conditions almost as cold as anything we can achieve in our laboratories. These cosmic refrigerators don't use laser cooling or magnetic trapping. Instead, they rely on the simple expansion of gas clouds, which cool as they spread out into the vacuum, approaching temperatures that make Antarctica seem tropical by comparison. Yet for all the cold that exists naturally in space, human beings have managed to create temperatures colder than anything found anywhere in the known universe. This remarkable achievement speaks to something profound about our relationship with the physical world. We are creatures made of warm flesh and flowing blood, evolved on a planet with a comfortable average temperature, and yet we have learned to create conditions more extreme than those found in the vast emptiness between galaxies. This ability to exceed nature's own extremes has opened doors to understanding that were previously locked away. When we cool matter to temperatures measured in nanokelvin, billionths of a degree above absolute zero, we're creating conditions that allow us to observe quantum mechanics in slow motion. Atoms that normally zip around at thousands of miles per hour slow to a gentle drift. Quantum effects that usually happen too quickly to observe stretch out over seconds or even minutes. In this slowed-down quantum world, researchers have been able to watch individual atoms tunnel through barriers that classical physics says should be impenetrable. They've observed the formation of quantum vortices, tiny whirlpools in superfluid helium that carry precisely quantized amounts of angular momentum. They've created artificial magnetic fields using nothing but laser light, and they've built quantum gases that behave like perfect crystals made of pure energy. One of the most beautiful discoveries to emerge from this ultra-cold research involves something called quantum phase transitions. Just as water transforms into ice at a specific temperature, quantum systems can undergo sudden changes in their fundamental properties when cooled to precise temperatures near absolute zero. But unlike the familiar phase transitions we see in everyday life, these quantum transitions occur at exactly absolute zero temperature, making them accessible only through the mathematical models and experimental techniques that probe the deepest cold. These quantum phase transitions reveal something remarkable about the structure of matter itself. They show us that even at absolute zero, even when thermal motion has been eliminated as completely as possible, matter still retains the capacity for sudden dramatic change. It's as if the quantum world has its own weather patterns, its own seasons and storms, operating according to rules that are written into the fundamental constants of nature. The practical implications of understanding these quantum transitions are staggering. Materials that undergo certain types of quantum phase transitions can exhibit properties that seem to violate basic principles of physics. Some become superconductors that work at higher temperatures than should be possible. Others develop magnetic properties that could revolutionize data storage and computing. Still others exhibit forms of quantum entanglement that might enable new types of communication and sensing technologies. But perhaps the most profound aspect of absolute zero research lies not in its practical applications, but in what it reveals about the nature of information itself. In the quantum world that emerges near absolute zero, information becomes a kind of substance. It can be stored, manipulated, and transmitted in ways that have no analogue in our everyday experience. Quantum bits or qubits can exist in superposition states that allow them to represent multiple values simultaneously. Quantum entanglement creates correlations between particles that persist across arbitrary distances. These quantum information phenomena suggest that reality itself might be fundamentally informational in nature. The atoms and molecules that make up your body, the chair you're sitting on, the air you're breathing, all of it might be better understood as patterns of information rather than collections of particles. And at absolute zero, when thermal noise is minimized and quantum effects dominate, we can see this informational structure most clearly. The journey toward absolute zero has also revealed unexpected connections between seemingly unrelated phenomena. The same quantum mechanics that explains why helium remains liquid at the coldest temperatures also governs the behavior of neutron stars, those incredibly dense remnants of massive stars where matter is compressed to nuclear densities. The superfluidity observed in liquid helium finds cosmic expression in the interior of these stellar corpses, where protons and neutrons flow without friction through matter so dense that a teaspoon would weigh as much as a mountain. Similarly, the Bose-Einstein condensates created in ultra-cold laboratories share deep mathematical similarities with the Higgs field that gives mass to fundamental particles. Both involve the spontaneous symmetry breaking that occurs when a quantum system settles into its lowest energy state. Both create effects that extend across macroscopic scales, influencing the behavior of matter far from their point of origin. These connections suggest that absolute zero isn't just a temperature. It's a window into the unified structure that underlies all of physics. By studying matter at its coldest possible state, we're exploring the same quantum mechanical principles that govern black holes, particle accelerators, and the earliest moments of cosmic history. The techniques developed for approaching absolute zero have also led to entirely new ways of thinking about measurement and precision. In the ultra-cold world, scientists routinely measure time intervals accurate to 18 decimal places, distances smaller than the diameter of an atomic nucleus, and magnetic fields weaker than the Earth's field by factors of billions. These extraordinary levels of precision have revealed that the universe is far more delicately structured than we ever imagined. For instance, experiments with ultra-cold atoms have confirmed that the fundamental constants of physics are indeed constant, at least to a precision that would detect changes smaller than 1 part in a trillion. They've also revealed subtle effects predicted by Einstein's general relativity, such as the way that gravity affects the flow of time, even in the weak gravitational field at Earth's surface. But precision isn't just about confirming existing theories. The ability to control and manipulate matter at the quantum level, made possible by extreme cooling techniques, has opened entirely new avenues of exploration. Scientists can now create artificial gauge fields that mimic the electromagnetic fields found in particle physics, but using clouds of ultra-cold atoms instead of high-energy collisions. They can simulate the behavior of exotic materials that don't exist naturally, exploring their properties in theoretical detail before attempting to synthesize them in the laboratory. These quantum simulators represent a new kind of scientific instrument, one that doesn't just observe natural phenomena, but creates artificial versions of physical systems that are too complex, too dangerous, or too expensive to study directly. Want to understand how electrons behave in a perfect crystal at absolute zero? Create an optical lattice using laser beams and trap ultra-cold atoms at the intersection points. Need to explore the properties of matter under conditions found in the core of neutron stars? Use magnetic fields to tune the interactions between ultra-cold fermions until they mimic the behavior of nuclear matter. The ability to create these artificial quantum systems has led to a remarkable reversal in the relationship between theory and experiment. Traditionally, theorists would predict new phenomena, and experimentalists would search for them in nature. But in the world of ultra-cold physics, experimentalists can often create conditions that theorists haven't even thought to explore. They can turn knobs and adjust parameters in ways that nature never does, discovering new states of matter and new quantum phenomena that exist only in the laboratory. This experimental flexibility has revealed that the quantum world is far richer and more varied than anyone expected. There are quantum states that exist only when matter is confined to 1 or 2 dimensions. There are quantum phases that emerge only when particles interact in precisely controlled ways. There are quantum transitions that occur only when external fields are tuned to exact mathematical relationships. Each of these discoveries adds another piece to our understanding of how the universe works at its most fundamental level. And all of them depend on our ability to approach, but never quite reach, absolute zero. It's as if the universe has hidden its deepest secrets just beyond the edge of perfect cold, where they can be glimpsed but never fully grasped, approached but never completely attained. The story of absolute zero is ultimately a story about human curiosity and the drive to explore the impossible. It's about the recognition that sometimes the most profound truths are found not in the comfortable middle ground of everyday experience, but at the extreme edges of what's possible. And it's about the discovery that those edges, far from being empty or sterile, are teeming with phenomena that challenged our conception of what reality, our understanding, and expand can be. As we've seen, the journey toward absolute zero has taken us through realms where matter loses its solidity, where individual particles merge into collective quantum objects, where the classical rules of physics give way to the strange logic of the quantum world. We've discovered that even at the coldest possible temperatures, the universe retains a fundamental restlessness, a quantum jitteriness that ensures perfect stillness remains forever out of reach. But perhaps the most remarkable aspect of this journey is how it has changed our understanding of temperature itself. We began with the simple question of what happens when you make something as cold as possible. We've discovered that cold isn't just the absence of heat, it's a gateway to entirely new states of matter, new forms of quantum behavior, new ways of thinking about information and reality itself. The laboratories where scientists approach absolute zero are more than just research facilities. They're theatres where the deepest dramas of quantum mechanics play out on stages large enough for human observers to witness. They're workshops where the fundamental building blocks of matter are shaped and moulded like clay in the hands of cosmic sculptors. And they're windows into a realm where the impossible becomes routine, where the abstract mathematics of quantum theory becomes concrete, manipulable reality. In these spaces, cooled to temperatures that make the depths of interstellar space seem warm by comparison, we're not just studying physics, we're exploring the architectural blueprints of the universe itself, discovering the quantum mechanical foundation upon which everything else is built. We're finding that reality is stranger, more interconnected, and more fundamentally quantum than our everyday experience could ever suggest. And we're learning that the journey toward an impossible destination can reveal truths more profound than any arrival could provide. The unreachable nature of absolute zero isn't a limitation. It's an invitation to keep exploring, keep discovering, keep pushing the boundaries of what we thought we knew about the nature of existence itself. So as our exploration continues, as we delve deeper into this realm where quantum mechanics becomes visible and the impossible becomes inevitable, remember that we're witnessing something extraordinary. We're seeing the universe reveal its deepest secrets, 1 degree at a time, as we approach but never quite reach the coldest possible point in all of creation. This impossibility of reaching absolute zero isn't just a technical challenge. It's written into the fundamental mathematics of thermodynamics itself. The third law tells us that as we approach absolute zero, each additional step becomes exponentially more difficult. It's like trying to walk to the horizon. No matter how far you travel, the destination remains just as distant as when you began. But this unreachability has led to one of the most beautiful paradoxes in all of physics. The closer we get to absolute zero, the more energy it takes to remove each remaining bit of heat. At temperatures measured in microkelvin, millionths of a degree above absolute zero, scientists must expend enormous amounts of energy to cool their samples by even tiny fractions of a degree. It's as if the universe itself is protecting absolute zero, making it more precious and more elusive the closer we come to claiming it. Yet in this cosmic game of approach and retreat, we've discovered something extraordinary. The techniques required to get within billionths of a degree of absolute zero have created entirely new branches of physics. Laser cooling uses the momentum of light itself to slow down individual atoms. When a photon strikes an atom moving toward it, the atom slows down slightly. Billions of these tiny collisions can bring a cloud of atoms to a virtual standstill, cooled by nothing more than carefully tuned beams of light. Magnetic trapping takes this process further, using precisely controlled magnetic fields to suspend ultra-cold atoms in perfect vacuum, isolated from any source of heat or disturbance. These magnetic bottles can hold clouds of atoms at temperatures so low that their thermal motion slows to less than the speed of a gentle breeze. In these conditions, quantum mechanics takes complete control, and the atoms begin to behave in ways that would be impossible at any higher temperature. The most sophisticated cooling technique of all involves the quantum properties of different isotopes of helium. Dilution refrigeration exploits the fact that helium-3 and helium-4 behave differently at extremely low temperatures. By carefully managing the mixture of these isotopes, scientists can create refrigerators that reach temperatures measured in millikelvin, thousandths of a degree above absolute zero. These machines are marvels of engineering precision, requiring superconducting magnets, ultra-high vacuum systems, and vibration isolation so complete that they can detect the footsteps of a person walking in an adjacent building. The laboratories that house these cooling systems exist in a kind of technological limbo between the possible and impossible. They're filled with equipment that operates at the very limits of what engineering can achieve. Vacuum chambers pumped to pressures lower than the space between planets. Magnetic coils wound with wire so pure that a single misplaced atom could ruin their superconducting properties. Laser systems stabilize to frequencies more precise than the best atomic clocks. In these temples of extreme cold, matter reveals behaviors that seem to mock our everyday understanding of how things should work. Atoms cooled to nanokelvin temperatures move so slowly that you could outrun them on foot. Their quantum wavelengths stretch out until they're larger than the atoms themselves, creating conditions where the wave nature of matter becomes more important than its particle nature. At these temperatures, the distinction between individual atoms begins to blur. Quantum mechanics tells us that identical particles are truly indistinguishable, not just difficult to tell apart, but fundamentally identical in every possible way. When thousands of these identical atoms are cooled to the same quantum state, they lose their individual identities entirely. They become a single quantum object, a macroscopic entity that exists in a superposition of states, simultaneously here and there, moving and still, until the moment someone tries to observe it. This merging of individual atoms into collective quantum objects creates some of the most striking visual phenomena in all of physics. Bose-Einstein condensates photographed in these laboratories look like glowing clouds of pure quantum matter. They're not glowing because they're hot. They're glowing because they're coherent, like laser light made of matter instead of photons. These condensates can be shaped and manipulated in ways that seem almost magical. Researchers can create quantum vortices, tiny tornadoes in the condensate that carry precisely quantized amounts of angular momentum. They can split a single condensate into two parts, creating an interferometer made of matter waves that can measure acceleration with extraordinary precision. They can even create artificial gravity for the atoms, using laser beams to mimic the effects of curved spacetime predicted by Einstein's general relativity. And so we find ourselves at the end of this gentle journey toward the coldest place in the universe, a destination we can approach but never truly reach. We've discovered that absolute zero isn't just about temperature. It's about the quantum foundation that underlies everything we see and touch. Even in the